Hello, everyone. Okay, we're starting up a little bit late here. Hopefully, you've had a chance to work on this warm-up problem. Let's see what people said. That's the exciting thing. Responses. Okay, blank one, general. Find the general solution to solve a PDE like this one in the picture. So there's a PDE, it's got an equation-y part, it's got boundary conditions, it's got an initial condition. I think this is literally the one we did last time, or almost the same. Okay. Part one, find the general solution according to you guys. Use separation of variables to get two ODEs for the equation. Set up an eigenfunction problem. It will depend on the boundary conditions or boundary condition of the PDE. Combine using the superposition principle to get the general solution. Part two, solve for the coefficients. Plug in the initial condition or initial conditions to get an equation involving an infinite sum. And the last part, find the coefficient Cn by Fourier series. Although this one was a little spread out. Maybe people didn't get to that one. So I think you guys are perfectly correct. Let's go through the correct answer. So general solution, yeah, that's what we're doing. First you find the general solution, then you find the coefficients. Excuse me. It's the same as all the equations we've been doing before. Separation of variables, although I guess I spelt it wrong. Maybe somebody else spelt it wrong. I mean, this is perfectly correct as well, the second answer. Let's Google it. How do you spell separation? Maybe tell me in the chat. How do you spell separation? Someone figure that out. Okay. Boundary conditions. So most problems have two. There's one at the left and one at the right. So this is at x equals 0 and pi. Okay, someone says it's with an A. Okay, so I guess this is the right way to do it. I spelled it wrong. My bad. If you're one of these 11 people, then you are like me and got it wrong. Okay. Spelling doesn't count in math. Okay, keep going. Boundary conditions, I think is more correct because there's two. There's one at 0 and pi. If you said boundary condition, it's not super wrong, but it's good to know there's two. In other problems, there might be more than two, but in these problems, there's always two. Initial condition, or you could have said you plug in t equals 0. So by plugging in t equals 0, you make the initial condition appear. I wouldn't say that there's more than one initial condition. So initial conditions is misleading. For this problem really only has one initial condition. Blank 5. Yeah, so I'd say you could use Fourier series or inner products or inner product. So these 12 people got it right too. But yeah, okay. So what we're going to do today is we are going to do one of these. We're going to do, just like we did last time, it's going to have different boundary conditions. So for practice, we're going to go through all these steps and do one more. And then we're going to start the non-homogeneous things. So far we've only done homogeneous equations, which have boundary conditions with zeros. And then we're going to start chapter 11.2, which has non-homogeneous things. So that's what we're going to do today. So pretty well done on this question overall. And this is the problem we're going to be doing. It was the last one we ended on last time. So I have this equation, which is a line. So it's the initial condition u of 0x equals x. It's a line. And I have some boundary conditions that I told you here. So I want to make this clear. Last time I gave you guys a problem and I didn't tell you the boundary conditions. And I said, can you predict what happens? And the answer is no, because I didn't give you the boundary conditions. So it's like not giving somebody enough information to figure out what to do. Today, I've really given you enough information. So here I have the boundary conditions and the initial condition. You should be able to guess what it does. And so I think the way you should guess what it does is interpret it as like heat, and then use your knowledge of how heat works to say what will happen. And there's 4 options here about what it is, if it's tending to 0 or not, and if it's always a line or not. Okay, so I'll give you guys a minute to do that. And then we're going to start solving this. So if you want to jump into, instead of just guessing what it's going to do, if you want to jump into solving it, you can do that as well. Good time for questions in the chat for the next minute while I'm waiting for answers. People need a little more time? Let me add 15 seconds here. So try to guess what's happening based on your like real life intuition. I think it would take you a long time to actually solve it and then answer this question. We're gonna solve it in a minute, but it's good to know like what it does before you solve it. It's a good sanity check. Make sure you have the right solution. Okay. Okay, I think most people are in. Okay, let's do this by percentages. Pretty split here. So not a huge consensus. So tell you what, let's do the math first. We'll do the math first, and then I will reopen it, and we can see. So maybe the math will help us decide. And I do have an animation of this one, so we can watch the animation afterwards. So what we're going to do is we'll do the math, we'll get a formula, and then we'll try to interpret the formula and see if we can figure out these things. Okay, so we're just going to go through the steps from the first little bit on this equation. So from the first top hat question, what do you do? The steps are general solution, and that's by separation of variables. That was the first kind of thing you got to do. This is going to involve a boundary value problem. Boundary value problem. And the second step is solve for the coefficients. And this is going to be a Fourier series type thing. So that's what we're going to do. Let's look at the equation we have. I'm looking at it in top hat to make sure I have it right. So it's this is the heat equation, and the boundary conditions, always very important. Partial xu at t0 equals 0. This is x equals 0. Partial xu of t2 equals 0. I'm going to write this as x equals L. I'm going to make L equals 2, so I can do everything in terms of L. And there's an initial, these are the boundary conditions, BCs. There's an initial condition. U at t, let's do this right. U of 0 comma x equals x. So this is at t equals 0. Okay, that's the problem we got to do. So the first bit is the separation of variables bit. This will be identical to last time. So we're just going to try a function u of xt. It's going to be, I'm writing t and x. Let's do it the other way. U of tx is equal to some function of x times some function of t. And then if you do ut equals uxx, let's do it this way. So this part is identical to last time and shouldn't be very surprising. You get f prime times g equals f of x times g prime of t. So there's one time derivative. I did flip it around here. There's one time derivative that's here, that's the g prime. There's two x derivatives that's here, that's the f double prime. And this means that f double prime over f is equal to g prime over g. These are functions of time. These are functions of x. And now is the separation of variables trick, which is because this is a function of x, this is a function of t, they have to be constants. So that means that you get two equations, f double prime of x over f of x equals minus lambda, and g prime over g equals minus lambda. Those are the exact same equations we got last time. So far, the separation of variables is exactly the same as what we did before. That's because so far we've only used the equation, we haven't used the boundary conditions. We're about to use the boundary conditions now, and you'll see some different things are going to come out. Okay, so the time part, time equation, g prime of t over g of t is minus lambda. That's the same as before. The solution is g of t is c times e to the minus lambda t. That is always the easy part. The hard part is the space part, and that has a boundary value problem. Yeah, let's write it like this. Time part, space part. So this is f double prime of x plus lambda f of x equals 0. And the important part is how these boundary conditions, how do these get converted? So, when you write this out, there's going to be a part that depends on g. So it's going to be g of t times something equals 0. G of t times something equals 0. But g is never 0. So the fact that you're multiplying by g doesn't matter. And the two boundary conditions should translate to f prime of 0 equals 0 and f prime of L equals 0. So that's what these two get translated to. Let's put them together so we can see. So this one gets translated to the derivative is 0, and this one gets translated to the derivative is 0. So last time it wasn't like that. Last time it wasn't the derivative, it was the actual value of the function. This time it's the derivative. Okay, so now you have to solve this. This is a 10.3. This is a classic 10.3 boundary value problem. Boundary value problem from 10.3. So you have to know how to solve it. You should go through all the cases, right? There's lambda less than 0, lambda equals 0, lambda bigger than 0. When lambda is less than 0, you get f of x is exponentials. So you can write it like this, or you can write it with hyperbolic cosine and hyperbolic sine if you want. But I think exponentials are fine. And then if you plug in these things, you'll get that C1 and C2 equals 0. So I won't go through the super details of this, but let me write BCs imply C1 equals C2 equals 0. So no good. So there's no solutions to when lambda is less than 0 except for the trivial solution. And by trivial solution, I mean that the function f of x equals 0 everywhere, and that's no good. Can you explain why this time it's the derivative involved in the boundary conditions, whereas last time it's the function? And the reason is it's just what is given to you in the problem. So in this problem, we were given these two conditions. So let me open it on Top Hat for a quick sec. And so that's someone told us in the problem, that's part of the problem is the boundary condition was these derivatives that was given to us. Last time it was a different problem that was given to us. So that's the reason why you get something else. So yeah, that's very important to pay attention to. In chapter 11, you're given the equation and also the boundary conditions, and the boundary conditions are just as important as the equation for what the solution is going to look like. Great, okay. So that's kind of similar to last time. Lambda equals 0 is the same kind of thing. You get f of x equals c1 plus c2x, and if you plug in the derivatives are 0, here's something interesting. I was about to say lambda can't be 0, but let's plug it in carefully and figure out what happens. So if lambda equals 0, the solution is c1 plus c2x. Let's plug in these two conditions. The conditions are about the derivative. So the derivative is c2. And so saying that the derivative is 0 at 0, or saying that the derivative is 0 at L, that means c2 equals 0. But that's not the 0 solution. So that just leaves f of x equals c1, and that is a perfectly valid solution. That is a constant function. Does the constant function with lambda equals 0, does it satisfy this equation? Two derivatives plus lambda times the function equals 0. Yeah, because lambda is 0. So, okay. So this is good. This satisfies the equation. Does it satisfy the two boundary conditions? Yeah, the derivative is 0 everywhere. So this is a totally valid solution for lambda equals 0. So there you go. That's one important difference between what we did last time and what we're doing now. Last time, all the eigenvalues were bigger than 0. This time, you can have lambda equals 0. So that is, different. In fact, if we go back to the Top Hat question, whether or not lambda equals 0 is an eigenvalue actually will answer part of this question. And that is because remember the eigenvalues tell you how these solutions behave in time. So the time dependence is this exponential e to the minus lambda t. So if you have lambda equals 0, that's one thing. If you have lambda positive, then it's something else. So they have different behaviors, just like we've seen in second and third order things. So I think if you're paying attention, you can narrow down, if based on this lambda equals 0 thing, you can figure out if it tends to 0 or not, based on what we've done already. So I will open that up again. Should I open it up now? Let's open it. I'll open it up now for another 30 seconds or something if you want to change your answer. So now that you know lambda equals 0 is an eigenvalue, maybe it changes your mind. So I'll explain that in more detail later, but I'll give you a chance to do it first. Okay. Okay, that was lambda equals 0. That was exciting. I forgot that was a valid answer. When lambda is bigger than 0, this is sort of the main case, like the like most important case you're going to get. And you get the solution, f of x is sines and cosines, c1 cosine of square root of lambda x plus c2 sine of square root of lambda x. That's f. The boundary conditions depend on f prime, so I'm going to do f prime here. F prime of x is going to be a combination of sine and cosine again. c1 square root of lambda sine of square root of lambda x, maybe with a minus sign. And the other one is going to be c2 cosine, c2 square root of lambda cosine of square root of lambda x. So I just did the derivatives here. And why did I do the derivatives? So I can plug in 0 and L. F prime of 0 equals 0. So when you plug that in, the cosine term will be non-zero, and so c2 must be 0. So this implies c2 equals 0. So that's the same as what we did last time when we plugged in f of 0 equals 0. So the cosine terms are often 0, but the cosine term in this case is the c2 term. Last example, the cosine term was the c1 term, and that's because of this difference of doing the derivative or not. So I'm plugging into this equation, and so the non-zero term is c2. Maybe it was lazy of me to skip this step here. Maybe I should write it out. So you really should plug it in. The first term will disappear. Then you'll be left with c2 times the square root of lambda times the cosine of 0, which is 1. And so that'll mean that c2 times square root of lambda equals 0, but lambda is bigger than 0. So, there were like a couple little steps to go from here to here that I skipped over. Maybe you should do them, write it out long. I don't know. It's up to you. Okay. F prime of 0 equals 0. That's c2 equals 0. The last thing is that the f prime of L equals 0. And this means that, seeing as how c2 is already 0 from this equation, this means that c1 times the square root of lambda times the sine of square root of lambda times L equals 0. That's the important equation that you get, I guess, with a minus sign. And this is the exact same kind of thing we got before. Lambda is bigger than 0, so this is not 0, this isn't 0. So that means that c1 can be anything as long as the sine of square root lambda L is equal to 0. So this gives you the squarey type solutions for lambda. So n times pi. So when is sine 0? It's at 0 at multiples of pi. So this, whatever is in here, square root of lambda times L must be n times pi. And that gives you the values of lambda. So yeah, let's write it right here. Maybe lambda equals, rearrange this equation, n pi over L squared. Okay. That was kind of similar to last time, but what will be different is what is f. So lambda is equal to n pi over L squared. But when we did our solution, let's see if I can straighten this up a bit. We had c2 equals 0 and c1 equals anything. C1 equals any. And when you plug in C2 equals 0 and C1 is anything into the equation, into here, for what is f, you get that f of x is equal to C1 times the cosine of square root of lambda times x. So last example, the solutions were the sines, and this time they were cosines. Okay, there's a couple of questions in the chat here. Oh, maybe you guys are answering each other's questions. Why does setting where sine is equal to 0 find the non-trivial solutions? Okay, yeah. So this is, this is supposed to be from 10.3, and I think in the chat someone indicated the right idea. We're looking for non-trivial solutions. So C2 is already 0. If you found a solution where C1 was also 0, that would just be like a boring solution. That would be f of x equals 0. That's like the case lambda less than 0. The only solution is C1 and C2 are 0, which is boring, no good. We're looking for a non-trivial solution. So we're looking for a solution where C1 is not 0, because C2 we already found was 0. So how could it be that C1 is not 0 as a solution? Well, if C1's not 0, then the rest of the stuff better be 0, which is how we got that the sine of this stuff has to be 0. So that's the logic kind of spoken out loud. You can also check, I think, go read the notes for 10.3. That's also where this stuff is. So in chapter 10, we just did this like building up of material that we're using now. And the whole point of chapter 10.3 was to prepare you for this moment. So yeah, that's where it would be to check. In chapter 11 in the textbook, they just say like, here's the solution, and then they move on. So, it's good to know. Okay, so the solution is cosines. The g of t function, right? G of t, that's the time function, was c e to the minus lambda t. Just like before, these both have constants, but we're multiplying together, so there's really only one constant. And so the solution that we're looking for is f of x times g of t. This is the solution, which is c times e to the minus lambda t times the cosine of square root of lambda x, where lambda is this thing, n pi over L squared. That's the solution we found. This works for any value of n. Any value of n. So as long as the sine is 0, that's where it came from, it works for any value of n. And in fact, I will say, here's another difference between what we did before and today, is because lambda equals 0 works. In the last class, we started at n equals 1, and we said, look, you need to have lambda bigger than 0, so n better be at least 1. But in this class, because lambda equals 0 works, you can use n equals 0. So you could do n equals 0, 1, 2, and so on. And when n equals 0, you get the cosine of 0, which is a constant anyway. And so that encapsulates the lambda equals 0 solution. So this is, I think, the solution we found by separation of variables. And again, I condensed down from 2 constants down to 1 constant. Usually this constant, we call it Cn, because it goes with the n that we had up here, just labeling it. And sometimes people call this lambda n, so that's another thing you might see. Lambda sub n depends on n. And the general solution is not this, but is the superposition of this over all values of n. So the general solution is the sum, n equals 0, 1, and so on, of Cn e to the minus lambda n t cosine square root of lambda n x. So the difference between last time and today is that we have cosines instead of sines, and we're starting at n equals 0. And the starting at n equals 0 makes a big deal, and that's because one of the eigenvalues is 0. So another way to write this out, like we did before, this is the formula, and when you're analyzing what the solutions do, it's helpful to look at what is the biggest eigenvalue, what is the second biggest eigenvalue, and so on. So I think another way to write this is like this, C0 e to the minus, and lambda 0 is 0, so you get e to the 0t, 0 times t. Cosine of 0 is a constant, that's 1, plus C1 e to the minus lambda 1t. So last time the dominant term was the sine thing, but this time the dominant term is a constant. This is a constant, C0. Okay, so the dominant term here is a constant. So if somebody says, what is the general behavior? Does it tend to 0 or not? Last class, all of the terms had a negative exponential in front of them. This class, this leading term does not have a negative exponential, and so it does not tend to 0 as time goes to infinity. So I'm curious to see what people said. So yeah, 48% of people... Oh, 48% of people think it does tend to 0. So look at that. It's either B or D. The answer is it does not tend to 0 because of this term. So the leading term is a constant. So what is the behavior of the whole thing? All of the terms except for this first term go to 0, but the first term will always stick around forever, and that is why the whole thing won't go to 0. Yeah, someone said in the chat, why do we start at 0? I think it really happened because lambda equals 0 was a valid solution. So this thing, there's no negative eigenvalues, but these were there. These were both valid. And in the last class we did it, lambda equals 0 was not valid, but in this one, lambda bigger than 0 and lambda equals 0 are both valid, and that's why we had starting at 0. So lambda equals 0 was legit. So that's why we're starting at 0 to encapsulate this term. Yeah. Yeah, so to find the solution, I would say, someone's asking about the superposition. So I would say what we did is we did this whole thing. We got to this particular solution, which is a separation of variables solution. It's a function of t times a function of x. So that whole thing was one kind of shebang, and we found lots of different solutions because there were lots of different possibilities for this lambda. So here we found infinitely many different solutions to the problem, and here we have combined the infinitely many solutions together using the superposition principle, and that is the general solution. So that's how we used superposition to go from, I guess, a solution, this was a solution, f of x times g of t, to the general solution. And you'll notice the n's mean different things in here. So here n is in the sum, and we're summing over all possible values of n. Here n is one particular value, so like, some fixed number, where here we're going over all of them. Okay, so I'm really excited. You guys most people got this question wrong because they thought it tends to 0, which it does not. So now you got to decide, do you think it's always a line or not? And I guess you can look at the formula if you want. Maybe you can see, like, when I run this, I'm going to show you the animation on to answer this top hat question. You'll be able to see, like, really what it looks like, and it looks like something familiar. So see if you can guess what it looks like when I hit play. So let me open this back up for another minute or whatever, so you can try to guess if you think it's B or D. And then I will run the solution. Oh, it closed itself. That's not good. How are you supposed to tell how the heat equation behaves without solving it at all? So you can interpret the heat equation in terms of like how you know heat flows, and then you can use your intuition about what you think is going to happen. So, that's what I was expecting you guys to do, but I thought since people didn't get it right, we'll try to do it by math. So here's how I would have done this problem. Having these boundary conditions, so the boundary conditions were the derivatives are 0 at either end. Let me see if I can put the original boundary conditions there at the very top of the screen. Yeah, I don't know which part you guys want me to show, but okay. So the original derivatives, the original problem is the derivatives are 0 at either end. That means a bar with insulated ends. So if you have a bar with insulated ends, and it's really hot on one side and it's really cold on the other side of the bar, what happens as time goes to infinity? Well, the whole bar should equalize and have the same temperature at the end of the day. And that temperature won't be 0, it'll be sort of the average value of the bar. So if you had that interpretation, then I think you could figure out that this thing we did with math, that the C0 is there. The C0 is going to end up being the average value, the average temperature of the bar. So yeah, that's how you know it doesn't go to 0. In top hat, I was also asking, is it a straight line or not? And I think if you look at it and see, is it a straight line? A straight line cannot possibly satisfy the boundary conditions that the derivatives, the x derivatives, are 0. So the only line that has x derivatives equal to 0 is a flat line. And so the answer is it's not always going to be a line, because a line won't be able to satisfy these conditions. So the correct answer is D. Let's see how many people got it. Most people got it. That's great. That's very good. Okay. So the answer is it's not always a line. In fact, it's going to look like a constant plus a cosine. It's going to look like a cosine function after a very short amount of time. All of these other terms that I wrote ... for, those are going to be really small. It's going to really look like this: C0 plus C1 times the cosine with this exponential decaying term. So let's see if it really does look like that. I think I have it. I gotta close this here. So here it is in Desmos, and here if I hit the play button, we'll see what it looks like. And so our prediction is it's gonna tend towards a constant. Based on real life, that constant should be the average value of the average temperature of the bar. And other than tending towards a constant, it's gonna look like a cosine. Let's see if that's right. So I think that we got it here. Maybe I can slow this down a bit so we can have it go in slow-mo. So there is a time 0. And if you pause it a little time later, it looks like a cosine, and the cosine is sort of shrinking over time. And there are, like that's not exactly right. There are higher order terms, but the higher order terms go to 0 really fast. So you're kind of left with the first couple terms. Those are like tell you what the picture looks like. Okay. So we did step 1. In this general 2-step thing, we did the general solution with separation of variables, the boundary value problem. We did all that. Now you should solve for the coefficients with Fourier series. I'm going to do the quick version of that. So, you should feel free to do that slower on your own time. And that's because we did this problem already a few classes ago. So a few classes ago, we did the cosine series for the function f of x equals x on 0 to L. That was one of our examples. And we discovered that the series is like this. X is equal to 1 minus 8 over pi squared. There must have been an L somewhere. Let's figure out what that is in a second. And it was one of these things where it only is the odd ones. N odd. So n equals 1, 3, 5, ... And it was the cosine of n pi x over L divided by n squared. Okay, and it occurs to me there must be an L somewhere. I think it was... Maybe there is no L anywhere. Okay, now I'm worried that I have my notes wrong and there's a missing L somewhere here in this term. If you guys have notes you can check quickly, you can tell me. Otherwise, let me see if I can figure out a reason in my head, but I think this is a tough one to do. N squared pi. I guess n always comes with, I think there's an L. I think there's an L here. I think that there should be an L like that. Okay, so I think that was the formula we did a few classes ago. And now we're looking for this general solution. So we want to find this is at t equals 0. And we know how the general solution looks. The general solution is this cosine series, and in front of the cosine of something, you put e to the minus lambda nt in front of it. So what you can do is you can very quickly, you can take this thing, which is the cosine series for our solution. I had it right the first time. Okay, so let's cross this x out. All right, so I think maybe there's no L. So if you write it out like this, all you have to do to convert it into the equation is you put in front of every cosine, you put this term. So that means I think I can write it like this. U of xt is going to be 1 minus 8 over pi squared. It's going to be the same sum and odd, and is 1, 3, 5, and so on. The same cosine and things as before. Cosine of n pi x over L over n squared. And the only difference is that now I have this term, e to the minus, and it's going to be this stuff squared, n pi over L squared t. So to get from the initial condition to the solution, knowing the pattern, so because we found the general solution, we know the solution is a coefficient, this exponential, and this cosine, and we know the relationship between the cosine and the exponential is like this, the square root of lambda n and lambda n, where lambda n was this thing. I can recognize that immediately from this initial condition we did before, this cosine series, and so I can find the general solution. It just looks like this. So all I did was add in this exponential term in front of the coefficients. So I left all the coefficients exactly the same, and I just put in this term. And I can definitely check that it works, because if you plug in t equals 0 in this term, in this general solution, you get exactly that thing, and that's what I want. Shouldn't A0 be dependent on L? Yeah, I'm kind of thinking that this whole thing is only true when L equals 2. So let's do it that way. Let's make L equal 2, and the whole thing will work. So I think there could be some things that don't work out here. So I think this is all perfectly correct when L equals 2. So let's go with that. Yeah, I think we will go with that. And yeah, you should be able to check that this term in the front is the average value. This is the average initial temperature, and that's in the textbook as well if you want to see. So if you want, so you get this formula, C0 is going to be the integral of 1 times, let's call it u of x0 dx from 0 to L with 1 over L. So it's going to be the average value. In this case, the average value is 1. It's not always L over 2. The reason it worked out to 1 is because it was the function f of x equals x. So it's a very special function whose average value, the average of x from 0 to 2 is 1. But you know, if it was from 0 to 3, it wouldn't be 1.5. So it's not always L over 2. Don't think that it's this. It's the average of the original function, of the initial value function. Okay, we did that example in lots of detail, hopefully. So I did this a little sneak at the end here to go quicker. I think it's all correct when L equals 2. I think that's all I want to say about this example. I'll leave you guys a second for questions here. Wasn't the IC you gave us u of 0x equals 0? No, the initial condition is u of x0 equals x. One of the boundary conditions is u of 0, x t equals 0 when x equals 0. So don't mix up the boundary conditions and the initial condition. So yeah, the initial condition was x. I want to go to the next question. I want to go to this. Okay, so I'm opening up in Top Hat. I'm opening up questions. Apparently, I'm typing a question. Ask question. Post. Okay, but I'll also answer questions in the chat. Why did I multiply by this? E to the n pi. So there's a minus sign missing in the chat, but I multiplied by this because I wanted to make the solution look like this. So I'm looking for a solution that is of the form some coefficients times this exponential times this cosine. And so that is, I saw I had the cosines, I had the coefficients already, but I was missing the exponential, so I multiplied by the exponential to make it work. You could have done the whole thing by saying, I'm going to solve for what the CNs have to be. You should get exactly the same answer at the end of the day. So if you find this approach confusing of adding in the exponential to make it match, then maybe you should do the whole thing and try to find what the CNs are, and you'll see that it all works out this way. Yeah, someone is asking for more Top Hat questions. There is going to be at least one more. Let me sort by most liked. Why is lambda squared in the series? The reason, I would say the reason it comes out like this, so in the time value you have lambda, and in the space you have square root of lambda. And that's just because of the way the equation worked, where the equation had two x derivatives and one t derivative, and that's where these things came from. And sort of if you carry through the calculation, that's what it looks like. So whatever is in front of the time has to be the square of whatever is in front of the space. Yeah, so where did the e terms come from? So I think I tried to answer that. Maybe it was people coming up with creative ways of saying no. All right, I think I'm gonna move on. There was one other question in the chat. Yeah, someone in the chat also wrote, when lambda is 0, wouldn't the dominant term not depend on t? And I agree with that. So the dominant term is a constant. It doesn't depend on time. So it's just like having a 0 eigenvalue in some of the other problems we've done in 2 dimensions and in 4 dimensions. There's a term that there's many critical points. There's lots of constant values that are solutions. And depending on what your initial condition is, you'll tend to a different constant value, but that constant won't always be 0. Okay. So that was all sort of review stuff from last time. This week is the last week of content in the course. So there's 11.2, 11.3, and 11.5 that are still going to get covered in the course. But we have all this week and next week to cover them. So it's okay if we go a little bit slower. I thought we should do another example rather than like rushing through and starting to do other stuff. But 11.2 is what we're going to be starting now, and it's all about non-homogeneous things. So the first thing I have for you is a fill in the blank about the non-homogeneous superposition principle. So there's the blank is a short blank. You'll find a blank solution to the non-homogeneous thing. So that's open on Top Hat, and you can take a stab at it. I'll let you read it while I answer a couple other questions. What was the C0 formula at the end? Yeah, so I said C0. I said it was the average value of the initial condition. How do you find an average value? You do an integral, and then you divide by the length of the interval. So this will work out. And you might recognize this. This is the inner product. This is 1 over L times the inner product of the function 1 with the initial condition, ux0. So the reason this comes up is it comes up as an inner product. I skipped doing inner product. I wanted to do this thing where 1, that's where the average value comes from. So that is this average value thing. Someone in the chat also asks, are we covering waves? Waves are chapter 11.3, so that we will be covering waves after we do this non-homogeneous stuff. So that's coming soon. Okay. Back to the non-homogeneous superposition principle. Let's give you guys one more minute here. Yeah, somebody asked about the answer key for chapter 10 and 11. I have no idea if there's an answer key or not. So I don't know of one. Maybe it exists. A lot of the problems, especially like chapter 10, right? It's like coefficients of Fourier series, so you can use a computer or a calculator to figure them out. Same with chapter 11. Another thing you can do, like if you're solving these things, is you can put them into a graphing calculator and just see like if it looks right. So that's what I would recommend. But I don't think I don't think there's an answer key per se. Yeah, so office hours were kind of weird. I don't think it worked super well. So I think what I'm going to try to do is focus on Piazza. So if you have a question that will fit on Piazza well, definitely ask it there. Yeah, other than that, I'll probably I could do another office hour, or you could just email me like individually and we could set something up. But yeah, I'm not sure they work the way I think they do. So I'll think about that. Okay, let's see if you guys got this fill in the blank. Particular, I think that is a right answer. Yeah, you find a specific solution. Also, is like a synonym for particular. Do watch out if you broke particular solution, then it's a particular solution. So that's that's not quite right. So I think all 3 of these are mostly correct, but the first 2 are definitely right. And so what we're going to do to find the same exact thing is going to work for PDEs. The whole game is, can you hunt for particular solutions? And we're going to do one that's an easy one. The whole shebang in non-homogeneous things is, how do you find particular solutions? You're like a particular solution hunter. And in this problem, unlike the example we just did, the boundary values are non-homogeneous. So in the example we did today and last time, the boundary values were both 0. It was the value at either end was 0. In this one, the value at either end is 3 and 7. So on the left side it's 3, on the right side it's 7. Those are the boundary values. They're non-homogeneous boundary values. And I'm saying, can you find an easy particular solution to that? And there is one out there, and I even gave you a hint. So you should be able to find the particular solution for this one. So I'm going to try a solution. Try u does not depend on t. So I'm going to try some function of x only, and then the equation ut equals uxx. What does that become? What's the t derivative of this thing? Is just 0. 0. What's the xx derivative? That is f prime prime. So what function f prime prime equals 0? What function has two derivatives equal to 0? That's the function f of x equals ax plus b. So ax plus b is a perfectly valid solution to the equation. Very boring. Very boring. It doesn't depend on t, and it's a linear function. Let's see if people figure this out. Constant is a good try. Oh, a couple people figured out linear. Some people figured out ax plus b. Polynomial, I think, is a good general answer. Line, so all of these are good. Constant turns out not to be quite good enough. And the reason is because we have ax plus b, and we want to match the non-homogeneous boundary values. U of t0 equals 3. This is at x equals 0. And u of t5, this is at x equals 5, equals 7. And so to match these, you got two equations with two unknowns. You're going to get a times 0 plus b equals 3. You're going to get a times 5 plus b equals 7. And if you solve these, you should be able to get what a and b are. I think b equals 3, and a is equal to 7 minus 3 divided by 5, or 2 over 5. So there you go. So the solution that works is 2 over 5x plus 3, and that is a perfectly valid particular solution to the non-homogeneous boundary conditions. So this is a particular solution for boundary conditions. So we found a particular solution that matches these non-homogeneous boundary conditions. If somebody gave you a harder problem with these, you would find this, then you would have to do steps 1 and 2 like we did before. So this kind of thing, finding easy particular solutions and then adding them on, and then you reduce down to what we were doing before. So that's what we're going to do. This was for boundary conditions, and with boundary conditions, non-homogeneous boundary conditions, this line thing always works in the heat equation. So non-homogeneous boundary conditions are pretty easy. Next time what we're going to do is we're going to look at what happens if the equation is non-homogeneous. So what happens if you add on something here to the equation, ut equals uxx plus something else. Then we'll do that next time. So I think that's all I want to say. I think I have just the next slide is just if you have any questions, you can ask them. But I think otherwise we're going to stop there. And there's going to be some notes posted that will maybe help you with these things as well. Okay. Yeah. Yeah, I'll leave the stream up for a bit so you can take notes on the last part. And I can put this, I can open this up again. Someone asked about my dog. Yes, my dog's name is Pretzels. Okay, I think that's it. Seems like no questions about this last bit. 7 minus 3 is a good point. 7 minus 3 is 4, not 2. So that's good to know. 4. Thanks. Yeah, that is how you do 7 minus 3. Okay. All right, I'm going to turn this off now, but I'm going to leave the stream open for a bit if you can take notes or like rewind. Okay, see you guys on Thursday.